everyone. Well, this is our first problem. We're trying to go over L'Hopital's rule and some of the harder problems, but we're going to start off with one of the easier ones, just to make sure we understand the idea behind it. So, L'Hopital's rule is a little trick to help us do limits that we otherwise wouldn't really be able to do. And so the idea behind L'Hopital's rule is that if you have a limit of the form 0 over 0 or infinity over infinity, well, what you can do is get the limit of the derivative of the top, over the derivative of the bottom. Now this means not using the quotient rule, but simply getting the derivative of the top and the derivative of the bottom. Okay, so, well, the first thing that you need to do is to make sure, this is the most important thing, is you need to make sure that it really is of the form 0 over 0 or infinity over infinity. Otherwise you can't use L'Hopital's rule, and you need to check it every single time. It's really important. So here we're taking the limit as x approaches 0. So if we plug in 0, we have e to the 0, which is 1 minus 1 over 0. So this is 0 over 0, and this means we can use L'Hopital's rule. Okay, so that means that this limit, and usually when you use L'Hopital's rule, you put a little L and an H here, just to symbolize that you're using L'Hopital's rule. We're going to say this is equal to the limit as x approaches 0 of, we get the derivative of the top. Well, the derivative of e to the 5x, remember that's itself e to the 5x times the derivative of the top, which is just 5. So I'm going to write the 5 over here on the left side. And then derivative of 1 is just 0. And then in the denominator, the derivative is just 1. Now notice I didn't use the quotient rule. You just get the derivative of the top and the derivative of the bottom. And then you try to plug in the value. So in this case, 0. And what we get is that this limit is actually equal to 5. And that's it. So very simple little trick. Okay, so let's do another one. We have the limit as x goes to infinity of 11x plus e to the negative x over 7x. Okay, so remember the first thing we do is we plug in our value, and if we do that, notice that we get 11 times infinity. Well, this guy is going to infinity, and then e to the negative x, remember this is equal to, let me just rewrite this, the limit as x goes to infinity of 11x plus 1 over e to the positive x all over 7x. And okay, so this guy is going to 0, and the numerator is going to infinity, and the denominator is going to infinity. So I satisfy the L'Hopital's rule condition. And so then I can get the derivative of both the top and the bottom. Okay, so this is equal to the limit as x goes to infinity of the derivative of 11x, that's just 11. And then the derivative of e to the minus x, well, this is minus e to the minus x, because the derivative is just itself times the derivative of the inside, which is negative 1. Okay, and then the derivative of the denominator is just 7, And now if I take the limit as x goes to negative infinity, notice that this one still goes towards 0. And so what I'm left with is simply the 11 over the 7. And that's my answer. Okay, so in this next one, this is where things start getting a little tricky, because notice that if we plug in our value, we don't have the usual just a fraction where we're going to get 0 over 0 or infinity over infinity. Notice, let me rewrite this as the limit as x goes to 0 of 1 over tangent of x minus 1 over x. Okay, so what's going on here, what I have is this guy, 1 over tangent of x. Well, if x is going to 0, that means tangent is going to 0 as well. And so what I have is a situation where I have infinity minus 1 over 0. This guy's also going to infinity. And this guy's indeterminate, but it's not of the form, so it's not 0 over 0 or infinity over infinity. So I can't just get the derivative of the top and bottom of each one of these. What you have to do is get it into a fraction form, and then you can use L'Hopital's rule. So if you look at this, well, notice we have two fractions. We can put them together by finding the common denominator and then combining them. Okay, so notice that what this fraction needs is an x, top and bottom, and this one needs a tangent x, top and bottom. Okay, so what I have is this is equal to the limit as x approaches 0. Now I'm going to have one fraction. The denominator is going to be x times tangent of x, and the numerator is going to be x minus tangent x. Okay, so now notice that if I plug in 0 now, what I'm going to get is 0 minus 0, so this guy is 0 over 0 times 0 is 0, so then now I can use L'Hopital's rule. Okay, so in the next step, if I use L'Hopital's rule, I'm going to get that this is equal to the limit as x goes to 0 of the derivative of x is 1 minus the derivative of tangent is secant squared x. And then on the bottom it's a little bit tougher because I have to use the product rule. So I would have the derivative of the first, which is 1, times the second, which is tangent, plus the first, leaving it alone, times the times the derivative of the second, which is secant squared x. Okay, so then you look at this again and you try to plug in the value. So we need to plug in 0 into all these guys, all these little x's, and see what we get. Okay. So remember that secant is 1 over cosine. So what I really have when I see secant squared, I'm thinking of what's 1 over cosine squared. Well, cosine of 0 is 1. So what I have on top is 1 minus 1 over, this is 0, it doesn't matter what this one is anymore because I'm multiplying it by 0, so I get the denominator is 0, so this is 0 over 0. And what this basically means is that I've gotten to a new expression, but I can't finish the problem, so I have to use L'Hopital's again. And we can do that. We can use L'Hopital's more than once. So Okay, so if we use L'Hopital's rule again, so the derivative of 1 is nothing, but the derivative of negative secant squared of x, so we have to use the chain rule. And so what we have is minus, if we bring down the 2, and then leave the inside alone, so we have 2 secant x, and then times the derivative of secant, just secant by itself. So the derivative of secant, remember, is secant x times tangent x. And then on the bottom, the derivative of tangent is secant squared x plus, and then here I have to use the product rule. So this looks pretty bad, but we got to do what we got to do. So the derivative of this product is going to be 1 times secant squared x plus x times the derivative of secant squared x. Well, I already got the derivative of secant squared x up here. It's just this guy. So I get secant x times secant x times, oh sorry, I forgot the 2. I'm going to put it over here. 2 secant, 2x. So I brought the 2 down. And then secant x times the derivative of secant, which is secant x times tangent x. Okay, so this looks really, really ugly, but notice, before we even try plugging stuff in, is notice that there's these two secants are really, if you multiply them together, this is secant squared x. And then here, this is also a secant squared x. And these two we can combine into 2 secant squared x. And so what we can do is we can factor out a secant squared and get a simpler expression. So why don't we do that? So we're not using L'Hopital's rule again yet. But what we are doing is on the bottom, I'm going to factor out a secant squared x. So if I do that, I'm going to get, so this is 2 secant squared x. So if I factor out a secant squared, I'm going to get 2 plus, if I factor out this secant squared x, I'm just going to have 2x tangent x. And now I guess you could have factored out a 2 as well, but we'll deal with that later. And then on top, what I have is minus 2 secant squared of x times tangent x. And notice that these guys are going to cancel, and what I'm left with is the limit as x approaches 0 of negative 2 tangent of x over 2 plus 2x tangent x. Okay, and now if I plug in 0, what I'm going to get is on top negative 2, well, tangent of 0 is just 0, so I'm going to get 0 over, now this time it's 2 plus 0, so this is actually 0 over 2, which is simply 0. Whew, and we're done.